Good afternoon, faculty and students. Welcome back to the lecture session of the fundamentals of NC CNC machine tools. In earlier occasions, we had discussed about the basic concept of NC and the CNCs, their characteristic features, relative merits and demerits, what are the added advantages of CNCs over the NCs, key components, the different ways to classify NC CNC machine tool in terms of absolute and incremental programming mode, which is extremely important, that is the classification based on open loop and closed loop control system. Before that, we had also discussed about the what is called axis nomenclature, that is which would be the Z axis, which would be the X axis, and how to identify Y axis, and the servo mechanism, the functions of two different units of the machine control unit, which is DPU, that is the data processing unit, and control loop unit, and some major hardware modifications of the NC CNCs in comparison to the conventional machine tools. Some major modifications were replacement of the conventional screw or lead screw by recirculating ball screw to reduce the friction on the slides. The slides of the NC CNC machine tools are coated with polytetrafluoroethylene compound, and other modifications is the installation of NC CNC console. So these are the very fundamentals which we had discussed in the earlier 3 lectures. Now today we will go for the some calculations or the quantitative aspects of the NC CNC machine. In this regard, to start with, today we will discuss about the what is basic length unit of NC CNC machine tools, and most importantly, what are the different attributes of the parameters which ought to be discussed or to be considered to capture the precision in NC CNC machine tool. There are 3 prominent parameters. One is resolution, second is accuracy, and third is repeatability. So these 3 parameters together comprises or captures the precision of NC CNC machine tools. So let us first come to the basic length unit of the NC CNC machine tool. The basic length unit, that means the smallest programmable, that is the incremental movement of each axis, that is referred to as basic length unit. That means, suppose you are given a job, you would like to write a program for the say turning operation along the Z axis, that is along the length, say Z equal to minus 45.8. It is rather coarse.
46.
If you would like to take it much closer, then say 45.86, say, that means 2 decimal digit we can capture, whether CNC system or the NC system can understand this 2 decimal digit and implement the same thing as far as displacement is considered. Okay, if I think about 45 point or minus or plus, that is immaterial, 45.005, it may be too fine, which the system neither can understand nor it can implement. So in this regard, we have to identify or we have to calculate what would be the minimum incremental value, whether it is 0.01 or 0.05 or 0.025, as the case may be. It may assume some other values as well. So what is the minimum incremental or decremental value which the system can understand and can execute the corresponding command? That will be the basic length unit of the NC CNC system. Just for your better understanding, I would like to give one example, that if you think about your vernier caliper or micrometer, there is a least count. So that is the minimum dimension that that particular micrometer can measure, below which it is not possible to measure. Similarly, the concept of basic length unit is similar, but it is as regard to the implementation of the tool movement along any definite slide. Now there are 2 categories of machine tool. One category is NC, where there was no computer, mind that. Returning back to the your initial definition of NC, it is electronics hardware. That is why it is called hardware based NCs. In case of CNC it is software based. So for hardware based NC system, voltage pulses are utilized to cause motion, and one pulse causes an incremental movement corresponds to one basic length unit. So how to attain or how to compute what should be the basic length unit for a particular arrangement? What arrangement we do have? If you recall the open loop control system, it starts with a stepper motor. So according to your program, voltage pulses will be generated by the pulse generator. So there is a series of pulse train which will be input to the stepper motor. Stepper motor will keep on rotating depending on the pulse input. Just for imagine only one pulse is emitted, then stepper motor will undergo some sort of angular displacement. Now the stepper motor shaft or the output shaft is connected to the lead screw via another larger gear usually. So that we have to calculate what will be the corresponding rotation of the lead screw for very small amount of angular displacement of the stepper motor. So if stepper motor rotates by a particular angle, say 1.8 degree, afterwards during derivation we will consider it is alpha, which is popularly known as step angle. So if stepper motor undergoes alpha degree for one pulse, then what would be the corresponding rotation of the lead screw, where there is in between is a gear train or gear ratio of Rg, such that Rg is greater than 1. That means a larger gear is connected to the lead screw and a smaller gear is connected to the motor, so that eventually the corresponding rotation of the lead screw will be rather less. So it will be alpha by Rg. Now for one complete revolution of the lead screw, what will be the linear displacement of the slide? Just like a nut bolt system, it will be equal to lead or pitch. So 360 degree rotation of the lead screw causes p millimeter of linear displacement. So for alpha by Rg, what will be the corresponding linear displacement? So since it is not possible to provide the system at least not less than one pulse, so we have to calculate what is the corresponding linear displacement for one pulse input to the stepper motor. This is how we have to calculate the magnitude of the basic length unit. So anyway, I will be coming to later on. In software based CNC system, each microprocessor bit represents one BLU. In case of CNC, hardware is eliminated and most of the hardware is replaced by the software, and here microprocessor is at the control. So in computer, information are stored in the form of binary digit, that is what exactly is called bit. Okay, so information storage, information processing, all are carried out in the binary mode, which has got two extreme values, either on off or 1 0. Okay, so either 1 or 0. So at under minimum condition, any one bit position change takes place. Anything below that is not possible. Okay, so what will be the corresponding changes in the value for one bit change position? So keeping that in mind, we can have a general expression where you can define like that way. The one was hardware based NC, one pulse corresponds to or lead to the realization of one basic length unit, and similarly in case of CNC, one bit will be representative of the corresponding basic length unit. Okay, now we move to the another way to define the basic length unit. It is same, but typically we call it as a resolution when we think about precision. Resolution is the minimum incremental movement which the system can interpret and execute the corresponding motion command. It is same. So minimum incremental movement which the system can interpret. Okay, so the system will have to interpret, and at the same time the mechanical or the electromechanical system will have to execute that particular command. So that is what exactly is the resolution. Now we do have two different categories of system. One is open loop control system and another is closed loop control system. So first let us take the example of the scenario of open loop control system, where it is the linear travel by the side corresponds to 1 pulse. Okay, so the way I have told you, 1 pulse is input to the stepper motor. So stepper motor keeps on rotating by some amount. That will cause once again some fractional rotation of the lead screw, because in between there is a gear. Now 360 rotation of lead screw will cause p millimeter linear displacement of the nut or the table. So for alpha by Rg, what will be the corresponding linear displacement value? So eventually we will be in a position to correlate the final displacement which is possible on the slide by issuing 1 pulse to the stepper motor. So this particular approach eventually lead to the development of the expression resolution. Why it is 1, I will come to the second part later on. So for the timing, just assume resolution 1 is defined as P by Ns into Rg, where P is the pitch or lead of the screw, Ns is the number of steps of the stepper motor, and Rg is the gear ratio. Now let us have a suppose this is the stepper motor. So you have to recall the arrangement of the open loop control system. This is the output shaft. This is a small pinion. Now this is a large gear. This is the lead screw. Over which there is a nut, and finally there is a table. This is table. This is nut. I am writing in short. It is lead screw. So if 1 pulse is input to the stepper motor, now here this is identified as a Rg, that is the gear ratio. Okay, so just consider the alpha is the step angle. That means 1 pulse will cause the stepper motor rotor to rotate by say some amount, say alpha degree. If that is so, then alpha degree into number of steps, this will be equal to 360 degree. Okay. Now if motor rotates by alpha degree, what will be the corresponding rotation of the lead screw? Because there is gear ratio Rg. If it rotates by alpha degree, the motor, then corresponding rotation of the lead screw will be how much? Alpha by Rg. Now 360 degree rotation causes P equivalent to P millimeter linear travel. 360 degree rotation of the lead screw, that means 1 full circle rotation will lead to the P millimeter linear travel. So if alpha, so for alpha by Rg, what will be this value?
P by 360 into alpha.
Good. P by 360
then we put
into alpha by Rg. Now from this relationship, if you replace 360 by alpha by Ns, so 60 by alpha by Ns will lead to this will lead to P by Ns into RT. Clear? So that is the how the resolution is quantified. Okay. Now for closed loop control system, we have to extend the logic, but in a different way. Because of the fact, if you once again, if you can recall the arrangement of the closed loop control system, the stepper motor is replaced by the servo motor. And in case of servo motor, it requires continuous analog voltage. So unlike stepper motor, there is no provision of issuing discrete pulses. So it is a continuous voltage. So there is no possibility to identify or to calculate what will be the displacement for one pulse. In that case, some additional features or additional items are incorporated in comparison to the stepper motor, open loop control system. What are those? That is the feedback devices. At the end of the lead screw, to monitor the position of the displacement, some encoder is mounted. If you can recall the closed loop control schematic diagram, at the end of the lead screw, you will find there is a disc type of arrangement which is called encoder. Okay, so encoder construction is also to some extent similar to that of a stepper motor. It is basically a circular disc. It is basically a circular disc having a number of slots or evenly spaced, something like this. Anyway, this should be evenly spaced. So this encoder disc is mounted on the leads to shaft. So as the leads to keeps on rotating, this encoder disc having the slots will also keep on rotating. Now on one side of the encoder disc there are light sources and on the other side there are photocells. Okay, so as the disc keeps on rotating, the photocells will be energized intermittently because the light will pass to the transparent regions only, and in the opaque region it will not allow light to pass. So alternatively transparent opaque, transparent opaque, transparent opaque. So alternatively you will have number of pulses emitted by the encoder disc. So what is the, once again, what is the minimum number of pulses that you can count? Only one pulse, because a pulse cannot be subdivided. So what is the displacement that the feedback devices can monitor and measure for one pulse emitted by the encoder? So in this case, in case of closed loop control system, the resolution is defined in a different perspective. In case of open loop control system, it was through the stepper motor, but in this case it is expressed in terms of precision movement that the system can capture by the feedback device. Now whatever may be the displacement, that is possible to capture only by the feedback devices, and this encoder disc is the feedback device. So as it keeps on rotating, so pulses will be emitted alternatively, and what is the magnitude of the displacement which we can monitor, or the feedback device can monitor rather, for one pulse. So from the analogy point of view, logic remains same. In earlier case, that is in case of open loop system, it was for stepper motor, but in this case it is for the encoder or the feedback devices. So logic remains same. That is why your expression will be similar, but just to distinguish from the stepper motor, I have written P by NSE into RGE, where E suffix is mean for encoder. Okay. So number of steps of the encoder disk and gear ratio of the encoder disk. Here RGE is not same as that of the earlier one. In earlier case, the RG was for gear train between the lead screw and the motor. But here, to improve the resolution, so encoder disk will be fitted over here. Okay, and in this particular case, whenever we would like to introduce another gearing system, the encoder disk is not directly mounted on the at the end of the lead screw. Rather, it is mounted on another shaft through a gearing. If the encoder is mounted on a smaller gear, then for one complete revolution of the lead screw, encoder disk will undergo more number of rotation. Is it clear? If the encoder disk is mounted on a smaller gear and the lead screw is connected to a larger diameter gear, so for one revolution of the lead screw, encoder disk will undergo more number of revolution.
Yes, sir.
That means for the same displacement, it will emit more number of pulses. So more number of pulses means, suppose 100 pulse represents 5 millimeter, and in other case 10 pulses represents 5 millimeter. So for one pulse, in one case it is 0.5 and in other case it is 0.05. So which one is more precise? Definitely 0.05. So if we allow the encoder to rotate 10 times more, then we can have 10 times more precise resolution, and lesser value is or lesser resolution is always desirable, so that we can have very finer movement. That is why at the end of the lead screw, the encoder disk is not directly mounted, rather it is mounted through another smaller gear. In this case it is reversed. Okay, so the speed of the encoder disk is increased as compared to that of a lead screw rotation, so that more number of pulses are emitted, so that and eventually this will lead to the achievement of finer resolution. Okay, that is the objective. So that is why you just see, as I was talking about your example. Suppose this NSE, whatever may be the figure, I had considered 5 by 10, and in another example I took 5 by 100. Obviously the second one will give you the more precise value. So that is the logic of mounting the encoder disk on a smaller gear, so that it will have more number of revolution. So that is what exactly is the resolution 1 for the closed loop control system. Expression remains same, but it is expressed in considering the encoder or the feedback devices. Clear? Now coming to the another way to resolution, to define in terms of bits used in the microprocessor. In case of CNC, it is everything is processed and your values are stored in the form of binary. So microprocessor capacity depends on the bit storage capacity. Okay, if it is n is the number of bits, then since it is in the binary form, either 1 or 0, so there are only two possibilities, either 0 or 1. So that is why 2 to the power n is the numbers of control points into which the axis range can be divided. Okay, and if n is the maximum side displacement of the axis, then second way to define resolution, that is why I have identified as resolution 2, which will be equal to n by 2 to the power n minus 1. Okay, be careful, this 1 is not subtracted in the power. You calculate the value of 2 to the power n, then subtract 1. Okay, for better understanding, come to this one. Say 0. It is decimal. Corresponding 3-digit binary number will be 0, 0, 0. Okay, for 1, it will be 0, 0, 1. Suppose I had taken there 2 to the power n. Okay, usually the value of n 32, 64, 128, which is very common. Okay, but this sort of large number you cannot give for example. So let us take for illustration 2 to the power 3. 2 to the power 3 means how much?
8.
So 8 different combinations are possible. Here bit storage capacity is 3. Okay, and what are the values? Bit 0 and 1. Okay, so 0, 0, 0, 0, 0, 1. If you want to identify 2, then it will be 0, 1, 0. If it is 3, it is 0, 1, 1. If it is 4, how much?
1, 0, 0.
1, 0, 0. So likewise it will continue. Then 1, 0, 1, then 1, 1, 0, then 1, 1, 1. So 5, 6, 7, 0, 4, 5, 6, 7 to cover all these. All combinations. 1, 0, 0, then 1, 0, 1, then 1, 1, 0, then 1, 1, 1. So all sorts of combinations are carried out. You see how much I had taken. 2 to the 2 cube means 8. 1, 2, 3, 4, 5, 6, 7, 8. So 8 different combinations are possible. If 8 different control, these are called control points, end points. What are the different values you can capture? If it is expressed in the form of a scale, say this is so this is 0, 1, 2, 3, 4, 5, 6, 7. So these 8 different control points can be captured or can be represented by these combinations. 8, 1, 2, 3, 4, 5, 6, 7. 8 points are there. Now how many slots are there? If we would like to measure anything, so we require distance between the 2 points. So altogether, so 8 points will allow you to measure 7 different slots, 1 less. So 2 minus 1. This is what I had put in the general form. 2 to the power n minus 1, always less, 1 less. Now I have drawn arbitrarily. Now if this is your entire length of the bed, if the entire bed length is L millimeter, generically, so this L millimeter will be equally divided by these 8 points. So between each every point, what will be the distance? L by 2 to the power n minus 1. So that is how another way to define resolution in terms of bit storage capacity of the microprocessor. Okay. Now finally, one comes from the mechanical system. In the earlier relationship, it was P by Ns into Rg. So these are basically electromechanical system parameters. P millimeter, that is the pitch of the screw. Ns is the number of steps in the motor, and Rg is the gear ratio. But here resolution is expressed in terms of microprocessor bit storage capacity. This is required for interpretation and computation purpose, and that resolution 1 is required or relevant for implementation. So if there is a difference, system will be considered only the maximum one. Which one is maximum? That is why the final resolution is defined as, or the control resolution, L by 2 to the power n minus 1 and P by Ns into Rg, the max of these two. Just let me give you another example. Suppose if you are told to imagine or calculate without taking any pen, pencil or calculator, what is 1 by 100? 0.01. Now if you are told that you can calculate 0.01, can you draw a line of 0.01 millimeter? Why not? Because your muscle or mechanical accuracy will not permit you to draw such a small distance of 0.01 millimeter. So if it is possible that you can draw a line at least 1 millimeter, then there is as such no justification in imagining 0.01 or 0.001. 0.01, 0.001 you can calculate through your brain, but you cannot implement it. But in case of NC, we have to implement in reality. Unless the slide moves by 0.01, what is the necessity of defining resolution in the order of say 0.0001? That is why the final system or the control resolution is considered whichever is the maximum out of these two. One through microprocessor, another through mechanical system. In majority of the cases, if you take the reasonable value, if you take n equal to 32, it will be extraordinarily high, 65,000 something like that. So even if you take L as a 1 meter or 2 meter, so 2000 millimeter by something around 65,000, it will be very, very small. But if you take the reasonable value of P, NS and RG, RG may be 6 or 3 or 4, P may be 4, 5, 6, 8, NS usually is a 200. So you will get a rather reasonably higher value, which the system can implement and execute. That is why maximum of these two has to be set as a your final control resolution. Okay. So finally, for your understanding, basic length unit and resolution both are same. Now we will move to the next one. Accuracy. Accuracy is the worst case inaccuracy of the system. That is how precisely it means machine access can follow intended path to the commanded endpoints under load. Because the tool is supposed to be exposed to the severe condition while cutting. So it will be definitely under loading condition. So under loading condition, if you are interested to instruct the tool to move to a particular defined point and what value it can assume exactly during cutting, that difference is your level of inaccuracy. You want to reach somewhere, but eventually you land somewhere. So there is some error. So that is your inaccuracy. So that inaccuracy, lower will be the inaccuracy, higher will be the accuracy. Now we have to identify what are the sources of inaccuracies. So if you can identify the sources of inaccuracies and you can calculate, then we will be able to define the accuracy of the NC system. Now there are two sources. One from the machine tool, that is from the mechanical side. What are the probable reasons? Wear and tear of components, play between nut and screw, backlash in gears, temperature rise, deformation of components under load. So these are the some prominent adverse or negative consequences which causes inaccuracies. These are the very common, nothing abnormal. These are predominantly present in all sorts of mechanical systems. Due to prolonged use, whenever there is a meeting component, it will encounter some or it will undergo some wear and tear, which adversely affect the accuracy. Play between nut and screw. There will be loosening due to wear and tear with the passage of time. Whenever there are gears, there is a possibility of presence of backlash, which will also contribute to the inaccuracies. Other parameters, temperature fluctuations, because all the mechanical members undergo some sort of thermal deformation. Maybe insignificant but very small one, but still it contributes to the inaccuracy. So temperature rise we have to take it into consideration. And finally, the underload, when the tool is subjected to load, from your knowledge of machine design or strength of material, you know that under load it will have some sort of deflection. So that also cause inaccuracy. So these are the 5 prominent sources of inaccuracies of the machine tools. Another source resulted from the resolution, and the inaccuracy resulted from the resolution can be identified as a half of the control resolution. Now how to quantify? Come to the next one. Let us give some space. First one was sources of, first let us come to this point first. Half of control resolution. Half of control resolution, if you use the same scale, I am not taking 1, 0, say 1, then 2, then 3, then 4, let's say 5, 6, maybe different one. If you are told to measure a distance of 2.3, with this scale, there is no intermediate graduation, mind that. So what will be your reading? 2. If you are told to measure 3.97, what will be your reading? 4. That means your error in this case is 0.03. In this case, it is 0.30. So which intermediate value the error will be maximum? What would be the values? If I make it 2.40, error will be 0.4. If I make it 2.47, error will be 0.47. If I make it 2.5, or say if you are told to measure a value of 4.5, for 2.5 your reading may be 2 or maybe 3. Okay, in any case your error is 0.5. Here also you may be satisfied with 4 or you may be satisfied with 5. Error is 0.5. That is the highest. Because if it is say 4.56, then what would be the error? 5 minus 4.56, which is definitely less than 0.5. So for any intermediate value, either 1.5 or 2.5, say 3.5, you can have highest error. Now how this 0.5 comes? How you can represent 0.5 in terms of resolution for this particular scale? For this particular scale, what is your resolution? 0, 1, 2, 3, 4. You can measure only in multiple of 1. So your resolution is 1. Okay, any intermediate fractional value you cannot measure. You can measure either 1, 2, 3, 4. So 1 millimeter is your resolution. So 0.5, how you can write? That is the maximum error. Let's say half into 1. That means in generic term, half into your resolution. That is how, or that is why it is written as half into CR. That is one part. Regarding the mechanical inaccuracies, it is very extremely difficult to measure or to quantify what will be the total deviations or the inaccuracies for play between shaft and nut and screw, backlash in the gears or thermal deformation. Okay, but statistically it is found that a very good pattern is followed by these mechanical inaccuracies. If you measure those inaccuracies and plot it, you will find that all these errors follow standard normal distribution. Okay, and you are well aware that it is a very bell-shaped symmetrical curve. This is your mean and sigma is the standard deviation. So plus minus 1 sigma, that means 68.2% error can be captured within plus minus 1 sigma. Additional 27.2, that means 13.6 multiplied by 2. If you add with the previous one, then those portion of the error will be coming up within plus minus 2 sigma. And within plus minus 3 sigma limit, almost 99.67% error can be captured. Almost 100%, close to that. So the entire mechanical error can be captured or represented by plus minus 3 sigma. That is why the final accuracy is taken care of or expressed by combining together one from control resolution was the source that we had already calculated 0.5. In this case, generically half of CR plus 3 sigma. One thing you may argue that here it is written plus minus 3 sigma, but eventually when we are interested to express the accuracy, we have taken only the plus. Why it is so? If you consider minus 3 sigma, then from this particular expression, it may so happen that the magnitude of half CR and magnitude of minus 3 sigma cancels out each other, even if they are very high. Plus 5 minus 5, it will be 0. Plus 100 minus 100, 0. Plus 0.001 minus 0.001, also 0. Although 0.001 is much smaller as compared to 100 or 50 or 75. So to avoid that, minus sign has to be dropped. Although both are present in significant proportion, but since one is positive and another is negative, as if they nullify each other because one is plus and another is minus. So when accuracy seems to be 0, but your significant portion of mechanical inaccuracy still exists. This is why while expressing the accuracy, you have to consider the worst case situation, and that is why the negative sign is dropped. So one source from the control resolution side, another from the mechanical side, and their contribution are clubbed together to have entire accuracy of the entire system. Clear? Now this 3 sigma is rather difficult. You have to take a lot of your data and you have to calculate mean, standard deviation, all these things. But for the thumb rule or for the simplification purpose, it is expected this 3 sigma value, if we can keep the 3 sigma value within half CR, then this half CR and quantity wise, this half CR plus half CR will yield 1 CR. That means the design of the machine to ensure that all the mechanical errors becomes equal to half CR, so that overall accuracy will be equal to the control resolution. Okay, so that is regarding the accuracy part. And finally, repeatability. As the name suggests, repeatability, that means if a particular command is issued and instructed to the machine tool system so that it would be executed several times, all under same or identical environmental condition, then the gross error that will be accumulated, that will be the measure of repeatability. The name implies how much consistent it is. You tell me to draw 100 millimeter line 20 times. I draw 100 millimeter lines 20 times. Sometimes you will find one line gives 99.97, sometimes it is 99.95, sometimes it is 100.2. So it is very difficult for any human being to draw. All lines are having identical length. So everywhere there is an error. So if you take the average of all these things, and what I told, or I was told, to draw a line of 100 millimeter, but if you take the data or average of all these actual drawn values, then that will give you the measure of repeatability. That implies how much consistent I am in drawing lines. Okay, in machine, if a particular command is executed several times under identical condition, the difference between the command value and the average of all executed values is referred to as the repeatability. So in this case, there is no difference in as regards your calculation part. Same thing, 100 millimeter or 200 millimeter, it is to be followed or repeated several times. So only mechanical error or sole contributor to the inaccuracy. That is why the repeatability is only stemmed from the statistical term. And in that case, we consider that as a plus minus C sigma. Okay, so that is, so we have started with the basic length unit, then resolution, accuracy and repeatability. This resolution, accuracy and repeatability all together captures the entire precision in CNC machine. Okay. Okay, so I believe that you have understood the basic concept of the basic length unit, resolution, accuracy and the repeatability. Two illustrative problems I have taken. A 2-axis CNC system used to control a machine tool table uses a bit storage capacity of 16 bits. That means, if you can recall the formula 2 to the power n, so that n now becomes 16. In its control memory for each axis, the range of the x-axis is 600 millimeter. That is, L is 600 millimeter, and for y-axis it is 500 millimeter. The mechanical accuracy of the machine table can be represented by normal distribution with sigma, that is standard deviation, as 0.002 millimeter for both axes. Now we have to calculate for each axis what is the control resolution, accuracy and the repeatability. So very simple. So directly you can apply L by 2 to the power n minus 1. So for x-axis, distance to be covered 600. So 600 by 2 to the power 16 minus 1, that is 0.0091 millimeter. And for y-axis, the length coverage is given 500. Since the same microprocessor bit is used, the denominator will remain same. So this calculation will yield the value of resolution as 0.0076 millimeter. Coming to the accuracy, half CR plus C sigma, not plus minus, be careful. Sigma is told as a 0.002. Okay, so to calculate for x-axis, because since the CR is different, for x-axis resolution is 0.0091, so we have taken 0.0091 by 2 plus 3 sigma. So this will give us a 0.0106 millimeter. And similarly for y-axis it is 0.0076 by 2 plus 3 multiplied by 0.202, that is 0.0098 millimeter. And repeatability, it does not depend on the resolution, it is purely statistical. So in this case you have taken 3 into 0.002. It is for both axes. Second problem, a CNC system is a bit storage capacity of 16 bits in its control memory for each axis. The range of the x-axis is 800 millimeter. The mechanical accuracy of the machine table follows normal distribution same 0.005 millimeter for both axes. The pitch of the screw used in x-axis motion transfer is 6 millimeter. The stepper motor is having 150 steps and the gear ratio is 3. So in this case, whatever we have to calculate, it is confined to the x-axis only. But from the given data, it is possible to calculate resolution 1 as well as resolution 2. Then you have to compare which is the maximum. So final system resolution will be the maximum out of these two. When all sorts of data are given, be careful for GATE or something like competitive examination or MCQ. If the sufficient data are available, then you have to calculate both resolution 1 and resolution 2 and compare. So first, P by NS into RG, that is the resolution 1. P was given, you see, pitch is 6 millimeter, number of steps of stepper motor is 150 and the gear ratio is 3. So P by NS into RG will give you 0.0133 millimeter. And resolution 2, that is the microprocessor system, L by 2 to the power n minus 1, this much. So now you compare out of these two, which one is maximum. First two digits same, then 3. So control resolution would be maximum of these two, that is the 0.0133. So accuracy, finally once we set 0.0133 is the final system resolution or the control resolution, then accuracy will be calculated based on that particular CR. So out of these two, I have selected 0.0133 by 2, and sigma is given in this problem is 0.005. So 3 sigma, so this will yield 0.0216 and repeatability as before, simply CCT mark. Okay, so these problems can be coupled with some other topics which we will discuss or which will cover up in the next 1 or 2 classes. Okay, so thank you very much for your patience hearing. That's all. If you have any queries, you can ask. Okay, or we can discuss afterwards. Thank you once again.